Yeah, so thank you very much for the nice introduction. I think this is quite true. Thank you also for the invitation to speak here. And the talk is about towards correct supercomputer general purpose problem solving skills. Actually, what we want to build in bilateral AI is broad AI. So we want to move from narrow AI applications to a broad applicability of artificial intelligence, and that's about. So when I talk about applications, I'm talking about optimization, configuration, engineering, and design of systems and processes. So, for example, building very complex electronic systems, for example, railway safety systems, as we did at Siemens, or compressors, or designing chips, or finding, let's say, schedules, which are as good as possible for manufacturing or in the area of logistics. Okay, what we need in these application areas are solutions which are correct. Okay, so when we configure a system or assemble a system, let's say in a safety domain, of course you want to make sure that this system is working. Okay, so correctness is a very important feature. So the state of the art in I would call it human engineered AI is that we have still the domain experts that describe the problem. We have a very lengthy discussion between AI and computer science experts with the domain experts, and eventually they implement a problem-specific AI, which then is used. So they're exploiting formal specifications, examples, drawing tables, also natural language descriptions, and eventually this problem solver then is used by users such that the problem instances are solved, hopefully with sufficient in a sufficient time and resources. So the point here is, so I quite remember very as it was yesterday, a discussion with Herbert Schreiner. He's sitting there. So I talked to him. Well, in how many cases you give the problem definition, just to the problem solver, push a button, and then it's solved. And he thought very lengthy, I have to say, and he came up with saying, well, in at most 10% of the cases. Which means that we are far away from the vision that the user just specifies the problem and the computer solves it. So actually what we have now is a heavily human engineered AI. Okay? And it costs a lot actually of time, and also money, to build these AI systems. So, and this can range up to several PhDs you need, to find algorithms and methods to solve actually the problem. Okay? So, what we want is some safe superhuman problem solving where we have the requirements that such an AI will deliver correct solutions, and such an AI should deliver better solutions than humans can. And I include also the algorithms which are designed by humans. Okay, so we want to improve the processes and methods human can do, okay, by AI systems. AI is very successful. If you look in the past, so we can significantly improve the solution quality. We can significantly reduce the software development and maintenance costs. However, what we want is that we substantially reduce this effort. So the goal is that we satisfy the requirements and we have zero development and zero maintenance costs. So this is the goal. So what we want is to move from human engineered narrow AI to broad AI. Okay? So that's the goal. So let me repeat the state of the art. So we have the sorry, I have to switch. So here we have the expert, and actually what we want is to replace these experts, which I would call something like an artificial engineer. So an artificial engineer which can be exploited to formulate specifications together with the domain experts. So the domain experts provide the formal specifications if there are some examples, drawing tables, natural language descriptions, also current algorithms. And then we use this artificial engineer to generate a problem-specific AI which is scalable. Okay, so which can deal with industrial-sized problem instances. What are we using? Well, on the side of the technologies, so we use for the generation of specification LLMs, slicing, testing, model-based diagnosis for query generation, fault discrimination. On the other hand, we have LLMs, graph neural networks, generation of problem-specific heuristics, code generation, code evolution, and also tweaking problem-specific logic-based solvers. Is this possible? So here is an example where we do some experiment in the area of large-scale configuration systems. And you see here two graphs. So here is the problem, the size of the problem instance. Here is time, and here is space consumption. And you see the traditional problem-solving methods are around here. Okay, and if we exploit the nature of the problem and the problem instances, then we can move far beyond. Okay, we can move far beyond. Please have a look here at the space consumption. Okay, so we can dramatically reduce the space consumption. And we have very promising new results, which are even better, so which can push the limit far, far more. But I have to say it's too early to talk about this. Hopefully we can talk about this in some months. But it seems that current AI technology really has the potential to generate these problem-specific AIs such that they scale with respect to the size. Thank you.
Questions?
Yeah, thank you very much for this talk. Maybe just a question. When you replace the AI engineer, so you mentioned several tasks there. One of them is the formulation of the problem, constraints and so on, and another one is generation of algorithms or heuristics or whatever. What do you think? Which phase is more difficult or will be more difficult for the computers?
Good question. I would say this depends on the problem. Yeah, I mean, for some problems it's quite easy to come up with a specification. For some problems it's extremely difficult, and the same also holds for the problem to be solved. Okay, so some problems are quite easy. Yeah, so where humans can generate quite efficient algorithms. Yeah, just in a short development time they need. Yeah. And other problems, you need, I mean, operations research literature is full with examples, where you need PhD thesis, to generate sufficiently good heuristics. Yeah. So I would say it depends. Yeah. Very more optimistic. For the current state, I'm more optimistic on problem-specific algorithms. Yeah, so there are tremendous improvements and results, even for MP complete and hard problems. Yeah, and I expect that if you look at polynomial problems, which are actually in many cases, you can find them in the industry, because then it should be even better.
Yeah, there is a lot of research going on now on this kind of explainable AI things. Right in the last weeks, if I think there was like the OpenAI publication on hallucination reduction, or there was the Thinking Machines Lab from Mura Murati who published this non-determinism defeating with identifying that the non-deterministic behavior of LLMs comes due to the kind of calculation method which is done in the GPUs and how they are synchronized. But so in general, my question would be, how do you think does this contribute to your approach? Because there is so much research going on now in improving the systems and make them more explainable. And I think this is the main ingredient, like to the automatic engineer you have seen. So what would be your expectation for the next years? What we can expect, what technology can do?
This is a very tough question. I made so many predictions which are complete rubbish. Yeah. So it's the big question if I should give predictions. I would say there are two sides. I mean, this so-called hallucination is not always bad, because it gives you creativity. If we have enormous large search spaces, yeah, actually we want to have this creativity, yeah, to find new ways, new algorithms. Yeah, so I think it would not be a good idea to cut out the creativity. Yeah, or how do you do this randomness? I think randomness is the key to find genius solutions. Yeah, I don't know. Some people are good in having, I mean, finding solutions by creativity, and so I think this is important. On the other hand, of course, we want to make LLMs more safe and avoid this hallucination. And I think there the symbolic part comes in. Yeah, where we can use the symbolic part. So my proposal here is that we use the symbolic part actually, or our specifications, yeah, to do the checking. So you have some sort of safety pack. It says, oh no, that's not good what you are generating. Yeah, so yeah, so it's hard to tell. Yeah, so in some cases, I mean, we will see how it will evolve. Yeah, but of course it all depends whether or not you are able to provide sufficiently good descriptions of your problem. Yeah, so in case you have tasks where you have a good description what the correct solution is, yeah, then creativity is a good idea because you have your safety pack, yeah, which tells you this is no good. Yeah, on the other hand, if this is not the case, yeah, then you want to cut out this creativity, yeah, and gear it to the right direction, this LLM. So yeah, but yeah, I'm not sure if my predictions are very difficult.
They certainly are. But let's move on and thank Gerhard again.